One general question from the auditory which I got for the email is about Fortran support. And I really want to have this conversation because it was not really intensive from any vendor and any presenter. So for Oak Ridge, he already sent me an answer about the programming the Fortran program with acceleration of GPUs with the help of OpenACC or OpenMP. So basically using directives approach. I think the similar conversation has been already put in place from Argonne side. So my questions to AI presenters. What is your position about Fortran programmers, particularly in a situation when you have HPC and acceleration through AI hardware? Who wants to answer?
Sure, well, are you sure you don't want us to sit down there? I'm happy to take the first swing at this. I used to work in Fortran, so I'm a recovering Fortran user. I think to be quite honest, right, our first focus was making the machine programmable with existing ML frameworks to sort of reach that broad user audience. And thereafter, we got a lot of pull from the HPC community. And the first instrument that we've developed to help reach that community is our lower level software development kit, the one that I mentioned in the talk, that includes a C-like programming language. So as soon as we did that, exactly what you might imagine happened, which is people asked us, okay, well, what about Python? What about Fortran? What about? And so our thinking now is, can we make effectively a mid-layer or an intermediate software layer between our lower level language and other languages, higher level, like Python or potentially even Fortran, that would make our system accessible without having to understand the details of the microarchitecture. And I think really that's our goal. From a product standpoint, the way I think about approaching that, and maybe Fortran in particular, is just to get a better understanding of who's using it for what kinds of applications and what segment of the overall user population that represents. So let me, so that's sort of a general answer, is sort of, we would approach it probably through our SDK, but I also want to turn the question back around on the audience. Maybe raise your hand if you're a Fortran user today, or if some of your work involves Fortran development, because that'll help me. That is actually more than I thought. Okay. Very cool.
And that's exactly in HPC we do care about Fortran.
Right. Yeah, that's really helpful. Cool.
Thank you. Thanks, Andy. Anyone else? Please.
Yeah, so I mean, I think it's just a bit more natural for some of these machine learning frameworks to be the first stab for a lot of the AI vendors. That is part of their initial story. Also, because of the data flow nature of PyTorch, TensorFlow, it's just easier to map to in a lot of respects. Because if you look at all the architectures, they're all kind of spatial in nature. Mm-hmm. That being said, I think ultimately all these vendors will inevitably actually start tackling the HP space in a more general sense. So we have to speak the language of the developers in that ecosystem. I think Fortran will naturally have to come with that. I would agree that ultimately we would end up creating this intermediate layer, just end up creating essentially a funnel at the top that becomes somewhat agnostic to your input language. And I think that would have to be coupled with a lot of the directives like OpenMP, some of these heterogeneous programming models, because it's just too hard of a problem to extract out the data flow that would come in that program. So we would need help from the users. I expect that to be inevitable as well. I don't think that's avoidable. Ultimately trying to get to the holy grail where you don't touch the Fortran code, but I think that's a long ways off. But I think we'll take baby steps towards that. I think it is something that is important to us.
Thank you. Anyone else? So let me go to the next. So the question has been to Oak Ridge about the file system. As I said, we do not have a person. The question to Oak Ridge about cooling subsystem, again, we will miss it. The question to Samsung, how do you have Semantica? So she's not yet here, okay. The question to Habana, are there some public numbers for the peak performance and TDP of Gaudi 2?
Can you repeat the question?
Yeah.
Can you repeat the question?
Yes. Are there some public numbers for the peak performance and TDP of Gaudi 2?
So peak performance in terms of teraflops, we have never published for any of our products. And again, the reason is because we target the training or inference of deep learning models. And so we publish performance numbers on training or inference of deep learning models. As far as TDP for Gaudi 2, I think I showed it in the slide, 650 watts.
Okay, thank you. The question to Cerebras. Has Cerebras revised their stand on MLPerf benchmarks? Any plans to participate and submit in the near future?
Sure. I'll first say that I think MLPerf is a really important community initiative. I was actually one of the early working group chairs that helped define some of the training metrics. So I think it's really important to have standards as a community, and we're happy to participate from that standpoint. Actually, developing a submission is a huge amount of work, as many of the people in here probably know. And some of the larger organizations that regularly participate have engineering teams that are dedicated to developing optimized performance implementations specifically of those models. I think that's just part of the nature of benchmarking, so it's more of a commentary. From Cerebras' standpoint, as a relatively small organization, our stance has simply been to focus first on our customers' sort of real-world model workloads, which is why you saw sort of the numbers that I put up today. They're not on sort of standardized, generic, representative implementations of models. Those are actual customer models. And that's just simply what we've chosen to focus on first, is ensuring that those run and that those run fast. I think that's also a little bit of a statement about benchmarking in general as well, because if you know those models and if you have your own work, you probably also know that the models that are part of MLPerf are not necessarily representative of the kind of stuff you might be doing, right? Which I think the benchmark will evolve to incorporate. But long answer short, we've chosen to focus first on customer workloads. That's all that is. And I think at some point we will submit to MLPerf. We don't have a committed timeline for it yet. But we're definitely still engaged with that community and looking forward to submitting in the future.
Thank you. So Semantic is here. The question to Samsung. How does one access the PIM risk instructions directly instead of using the optimized PyTorch or TensorFlow implementation from Samsung? Can domain-specific deep learning compilers directly make use of these risk instructions?
Yeah, so that's a great question. So firstly, these are RISC-style instructions, so they're 32-bit. And the reason we chose RISC is because we need a subset of operations. There's some very simple control flow, arithmetic, and data flow, like moves, fills, load type instructions. So yes, you can access them directly. There is a direct execution path. There are certain libraries that you have to link with compilers. It isn't very generic, full compiler support right now, like you can't just use LLVM and things like that. But there is, the software stack is evolving, let me say that. So at this point, the people who worked with it are using sort of the PyTorch and the plugins that Samsung has created, because it's really, it's through prototyping and it's through all of that, but I think the software stack will mature more.
Thank you. So the question is, if possible, I would like to ask the speakers about the OpenCL programming language. I may be wrong, but as far as I know, it was supposed to be the alternative to CUDA for non-NVIDIA GPUs, as well as on other architectures. However, it seems it is not going to be present neither on Frontier nor on Aurora, or everything seems to rely either on Cocos, HIP, Intel's One API, or the more limited OpenACC. Could the speakers make a comment about their current situation with OpenCL?
Want me to take it?
Yep.
Yeah, so SYCL is actually an extension to OpenCL. That is how we view it in Aurora, right? OpenCL is still supported in Aurora. You can still use it, but the catch is that the host code that is still supported, it's going to be like, up to the user or the application developer to focus on that. So instead of that, going with SYCL would be easier because you get a single host device accelerated language. So that's basically it. But you're welcome to use OpenCL. OpenCL runs well on Intel GPUs or for any other GPUs for the fact.
Thanks, Himesh. Other speakers?
So I would agree with that statement. I think there's been an evolution of OpenCL because the adoption of it has been somewhat mixed, I would say, because a lot of folks, they do find it a little bit too low level in terms of being able to program. And secondly, I think there's been a lot of baked-in assumptions into that programming model coming from more of a GPU mindset. So I actually see some challenges with the AI vendors to adopt that model for their devices. Maybe some subset. I know it's a open standard, so there potentially could be some evolution, but until that happens, I don't see initial adoption directly on the OpenCL side. More so on the evolution of what OpenCL will become. That's my general thought.
Thank you. Other speakers? No one else wants to answer this question. Okay, let's go further.
It's just that it was so well answered.
Each hardware vendor has a different strategy for addressing current performance limitations in computing. Why is their particular approach well suited for problems in scientific computing? What scientific applications would work particularly well for their solutions? And what types of applications do they think would see less improvement?
Is that a general question for everyone?
That general questions for audience.
Okay, I think, it must be evident from the Samsung presentation, we're really targeting the memory bandwidth bound applications, right? We posited a few AI kernels, the BLAST 1 and 2, that we know are memory bandwidth bound, but this is by no means the exhaustive space. I think there are a lot of HPC applications, science, even applications like, molecular dynamics, for example, lamps, they have phases which are very, very memory bandwidth bound. And, those are also good targets. So any place where you're looking for a bytes per flop, 1 and greater, for example, which is really hard to come by in the systems that we have today, I think you'll see value from the Samsung technologies.
I see. Thank you. Other speakers?
I can go next.
Yeah.
Right. So I think hardware always decides the kind of algorithms get picked up. Right. That's the hardware lottery. The way I see it for Sambhava systems, the advantages that we have seen are especially on the left and right side of the curve that we talked about in the presentation. So on the right side of the curve, you have these models that require a lot of memory. These could be your activation memory. These could be in terms of number of parameters, size of inputs, whatever they are. And when you sort of have to do this on, say, a GPU, you need an entire farm of GPUs so that just to get enough number of collective HBM memory to hold all of your parameters, your activations, whatever that might be. Whereas our solution can sort of give you a much simpler way of doing it. So that kind of from a deployment point of view makes it easy. And even with performance, you can use data flow architectures to hide some of these DRAM latencies and sort of get away with it. And on the left-hand side of the curve is more from not as much as scientific applications maybe. Well, actually even for scientific applications. So on the left-hand side of the curves are these models that are maybe deeper and skinnier, I have less number of layers, or even models like LSTMs, where you are consuming your previous output and you might have a lot of compute because you are executing on a long sequence, but you might not have as many sort of parameters required, so you can stay within your data flow compute graph. And even there, we sort of see a lot more advantages. So yeah, each hardware architecture will have certain things that they are good at, certain things that they are okay at. And then I think for Sambhava systems, these things we are extremely good at. And then for everything else, we strive to be really good at, or at least competitive at.
Thank you. Yes.
I wanted to respond. Thank you. I would say Habana made a very early bet on AI and deep learning, and that bet is definitely paying off. It is paying off within HPC only to the extent that HPC applications are, or rather HPC problems are being approached using AI deep learning models. I think we're yet to see how successful that AI first approach is going to be. We think it has a good runway left. I would say that Intel, as a larger organization, has a long history of doing experiments with dedicated products. And when those products succeed and they see a long runway, the intellectual property built into those products actually makes its way into CPUs and systems on a chip. So that's kind of a trend you may see in the future.
I see. Thank you.
One more on that one, if it's
Sure.
okay. So at Cerebras, I'll generally say we see tremendous, really transformative potential for AI for science, particularly at large scale. Just last week, I was at the University of California, Davis for a Department of Energy workshop on the future of AI for science and security. And that working group had a charter to think about what large-scale AI in particular could do for science and security, not next year or the year after, but 10 years from now or 20 years from now. So really on an ambitious scale, on a long-term timeline, similar to how we as a community built the exascale computing program. So it was really fascinating, and one of the themes I think is very well aligned with what we've done at Cerebras, which is these very large-scale, quote-unquote, foundational models for science. Right, in the commercial world, we've started to see a pretty inspiring capability of foundational models in language. Right, these are models like the generative pre-trained transformers, GPT models like GPT-3, where you can train them on a huge volume of unlabeled data, and they can learn in a semi-supervised capacity to a general set of tasks, and then be fine-tuned with zero or few shots to many downstream tasks. And so I think that that approach to learning with large volumes of unlabeled data and very large models that can be trained generally and then subsequently fine-tuned for a large range of tasks is very well suited for what we've built at Cerebrus, because these models are sort of scratching the surface of 1 trillion parameters, and we expect them to be in the tens of trillions or even hundreds of trillions of parameters in the next decade. That's the kind of magnitude of compute that I think isn't really well matched to traditional architectures or traditional clusters. It's going to require much more. And it's also going to require us to not only build larger models and make them computable in reasonable amounts of time so that we can experiment, but it's also going to require us to build more efficient models and more efficient ML using techniques, for example, like sparsity, which we've built into our hardware and ability to harvest sparsity at the hardware level from day one, because we acknowledge that AI is going in this direction. So the first thing I'll say from Cerebrus' standpoint is we think that there's a lot of excitement, and I think a lot of potential for solutions like ours for these very large-scale foundational models for science. The other thing that I'll say that isn't mutually exclusive from foundational models in AI is we've also seen extraordinary success, I think, in a relatively short amount of time, using our system for HPC workloads like stencil codes, FFT, other problems related to molecular dynamics or physics-based modeling or signal processing. And because of our architecture, have also seen some success at that intersection that I mentioned earlier in my talk, at the intersection of AI and HPC. I think in particular, and maybe this is also, I have to acknowledge my bias, a personal interest, I think there's a lot of really exciting stuff happening at that intersection of AI and HPC. And I think in part because of our system's ability as a generally programmable sparse linear algebra engine, its ability to execute both kinds of workloads at high performance, I think gives us a unique opportunity to help explore and open up that space of converged AI and HPC with Cerebrus systems.
Thanks, Sanjay.
Can I make a comment to their answers?
Yeah.
Can I make a comment to their answers? Can I make a comment to their answers?
Yeah.
Okay. So I think I've heard you guys' answers on this. So I'm still trying to understand the HPC and the AI ML convergence factor. So an example I can give you is ICF. And so in ICF, like the design of experiments and using predictive simulation capabilities that we have at the lab, and then building in the AI ML stuff. It's okay to say that you can generate millions of models on parameters, but to what degree are they feasible to tie that back into actually executing those experiments, which cost money? So what I'm trying to say is that you have something complicated like an ICF experiment, lots of different parameters that control the configurations of it, and then we have predictive simulation capabilities. So we have these codes that are leveraging traditional compute using the HPC, for example, like the exascale machines. But the idea there is that if we know certain input initial conditions, we can kind of predict what the result of that experiment will be like. But in my mind, I think what we should be doing is how do we use AI ML to not just generate, like a million different types of parameter configurations, because there is no informed decision that's coming out of there. So a lot of the stuff that I saw today was actually showing me like BERT and NP, the natural language processing stuff, but I didn't see a lot of overlap in terms of like actual practical applications where you're saying that you're working with vendors that actually have a design decision or a design configuration, and how are you guys actually leveraging machine learning to inform them of their optimal designs? I think a lot of it is like training and inference, which is I guess what I'm trying to ask is like how are you guys building the hardware in which it can actually integrate, with the predictive simulation capabilities and the experiments, so we can actually do we can actually have configurations that are meaningful and not just like, oh, we have a million configurations because we were able to like read the, do machine learning on a big data set. And the second point I wanted to make is the scalability studies that we were seeing on the Cerebrus machine. So the finite difference, that's a really good show point, but oftentimes you have multi-physics codes, and so you typically don't do finite difference schemes because they're very simple, and oftentimes like it doesn't work that way. And also the question there is like how is this? So a lot of ways we can use like these accelerators that we have on GPUs. So we can have like different applications that are multi-physics. They're leveraging what they need to. But have you thought about the case when you have a multi-physics code? How are they going to be splitting up these resources on these, these AI ML accelerators? So I didn't see any of that, and I don't understand how that is actually. When you guys were saying there's like HPC going on, but I couldn't see where that HPC was. So I'd like to get clarified on those points. Those, if from different vendors that are here. So thanks.
Sure. Maybe I'll try to knock on. I'll try to address each one of those, but feel free to follow up either here or separately if I don't. Maybe the last one first on the multi-physics and how to figure out the optimal mapping of compute on a heterogeneous cluster. That is, what part goes to the accelerator and what doesn't. That's actually something that we're working on right now. So we started with, quite frankly, sort of simple stencil-based codes and stencil-based representations of relatively simple algorithms like finite differences because it was a good place to start, and it's also something that several customers brought to our attention, right? But immediately after that, several customers asked us, for example, about supporting, two things. One, integrating that into their end-to-end workload. And even a relatively simple algorithm like that, there's still a question of, what do I offload from the rest of my workload? Or at what point do I offload that particular algorithm? How do I integrate it back in with my end-to-end software stack and the rest of my cluster? So we're working on, first, effectively productionizing even those simple algorithms in a complex heterogeneous cluster and workload environment for customers. The second thing is, multi-physics is not lost on us. I think there's some really scientifically and economically valuable problems in multi-physics that will require more complex implementations. And we have at least one project on that right now. But it's two things, honestly. It's not that mature yet, and also it's not yet public. But we're definitely interested in learning more about problems in that space. So then coming back to your first question, which I think you summed up at one point about sort of how are you building the hardware to integrate. And I think as you know, we've integrated our system now at Lassen effectively over an Ethernet to InfiniBand gateway because Lassen is an InfiniBand system and we're an Ethernet system. So we've sort of done the mechanical and the network integration, and are starting at a fairly simple level in terms of end-to-end workload integration, doing some early demos of simulation on Lassen, output to Cerebrus, feedback into Lassen. We're doing those demos now and planning to publish some of the results at SC22. But I think that's a much longer co-design process, right? Like we're excited to see that kind of thing happen, as well as the work that we did at A&L on molecular dynamics, HPC and AI. But I think, from my standpoint, I think we're just identifying that as an area that's rich to explore a little bit further. How can we make some of these expensive simulation problems and exhaustive experimental spaces more affordable and a little bit more narrow? It's definitely something we would like to do some more work on. But hope that helps.
I would just respond by saying I would give a +1 to what he just said. We're eager to work with the community to embrace the kinds of challenges you're describing. I've seen that sort of thing work at a relatively small scale with reinforcement learning, where there's basically an AI model that generates a prediction, and then that prediction is tested in a simulation environment. And today, it's as simple as running the AI model on an inference ASIC and running the simulation on a CPU or on a GPU. That can, of course, scale out in a variety of ways, and it'll have to for some of these HPC problems.
Other speakers? Okay, let's move on. So the question for quantum computing. Okay.
You activated? Oh, okay. Okay, I'm ready.
I lost that in my email. So basically the question has been if quantum computers are phonemic computers or not. If they are, how we can use the traditional memory like DRAM or HPM.
Okay, very interesting question. So we certainly are, but the problem is that the memory that we use actually is classical. And this is basically hybrid architecture. So way how it operates, you have a quantum algorithm, you convert it to a sequence of gates, right? It's all stored in regular memory. And after that, you just basically feed it to a quantum device, right? And basically on quantum device, we execute, and after that, we just make a measurement. And the result is also stored classically. In ideal scenario, you want to have actual quantum memory as well, but the problem is that the technology is still under development, and it's not quite there yet. So is it the answer?
Well, I don't know that answer, but whether this is a complete answer, it's very hard to say.
Yeah, so but basically this is how it operates right now. It's certainly not ideal.
Thank you. The question for Aurora. Will Aurora be included in Insight 2024? Is there a pie chart, distribution chart for different science areas that are being allocated to Aurora? It is interesting to know about the applications that are closest to demonstrating scalability to exascale already.
Yeah, I'm not sure you can answer that now. So, and again, that's a question to a different project team. I think leave it upon posted. We'll probably try to find the right audience to answer that then.
Thanks. The question for Cerebras again.
I can actually answer. I think I remember something else.
Sure.
Yes, so at the same time, we run certain non-normal architecture, right? Like MEM computing. I don't know if some people are familiar with. This is a new type of technology where basically what you do, you rely on self-organizing gates operations. So, and we do have actually early stages projects. We're actually thinking about how to implement these gates using actual quantum computing. So it's possible, essentially, whatever non-one-diamond architectures solutions exist right now, it's possible to rethink them and actually create quantum version of it.
I see. Thanks. So in the Cerebras presentation, a project at Lawrence Livermore with AI surrogate models was mentioned. It would be interesting to hear more about the simulation project and what the AI surrogate model is actually emulating.
Sure. Unfortunately, I think I'm probably the wrong person to answer that. But if the person's willing to identify themselves, I can follow up directly offline and give you a full rundown, hook you up with one of our team members who worked on the project, or find me afterwards.
Mm-hmm.
Sorry, not very satisfying. I know.
So a general question about the cost for switching technologies is very high. How can we tell that the difference between narrow commercial experiment and larger and permanent industry trends? Similarly, what we do, and could you give us some tips on how to avoid vendor lock-in?
I mean, if you look at what a lot of the vendors are doing, we are trying to support the standardized frameworks at the front, right? So
Mhm.
there is no lock-in from a programmatic point of view. Like, we're all using PyTorch effectively. So if you express your program in that way, it should map well onto the architecture below. So you're generally not locked in, I would say. I guess one interesting thing, and it's kind of related to the question before about what should we do with these things, is you can open up your mind in terms of going beyond what has been done in the past. So for example, some of the customers we're working with, when they're working on clusters of AMD processors, there's a cap to the size of the problem that they can solve for whatever reason. There's some sort of physical limitation or how things are connected. And then when they move to us, that cap is removed effectively. So really, the lock-in would happen because you're actually not able to solve something on another vendor. Like, it becomes impossible to solve it on the other vendor, which is generally just a good thing. And so with time, surely some of these incumbents will catch up. Maybe they'll solve those bottlenecks, but I wouldn't think of it as being stuck with it. It really opens up the funnel in terms of what you can do because it's such a different piece of hardware, and the way we approach things on our hardware is fundamentally different. It kind of frees you up to do new things that you couldn't before. But from a programmatic point of view, I don't think there would be very strong lock-in from that perspective, is my general opinion.
I see. Thank you.
I'll comment on that as well. As far as the cost of switching is concerned, there is always going to be some cost, and I think it's important to run experiments during the course of your evaluation to see what those costs actually are for your particular case. This is something we do constantly with customers and prospects before they actually purchase our products. In terms of whether the product is a corporate experiment or not, all I can say is, if you're concerned about that, then don't be an early adopter. Don't be the first person to buy a new hardware product. Go for, make sure some of your peers are invested before you do, or maybe make sure that a second generation of that product is going to be available, so you know that the company backing it is committed to it in the long term. And then in terms of vendor lock-in, I think you need to avoid non-standards-based work. That's a tricky thing to ask because a lot of these hardware architectures have specialized features, and unless you invest in those, which is essentially a way to be locked into that proprietary architecture, you're not going to enjoy the benefits. But again, perhaps waiting for something to be a little bit more standard may help you avoid some of that lock-in.
I see. Thank you.
Yeah, I just wanted to cast my support for Andrew and Milen's responses. I think those are spot on, particularly on vendor lock-in. I think we're all in this really to make platforms accessible, to accelerate research and development, and like locking you into a particular architecture doesn't actually help that. But there was another part to that question about how to tell if something's just sort of a unique unicorn, special snowflake example of a commercial product or a commercial application that might be idiosyncratic or not representative of a science problem, and how to try out hardware systems. I think we all have pilot and trial programs as well as systems at the national labs that are available for use for research and experimentation upon proposal. So I would just encourage everybody to get out and use our systems and help us together discover what are the long-term trends, because really I think that's a community effort to understand, what are going to be the neural networks of the future that are the architectures that are really the most transformative for science. We learn that by listening to you, our users, as you make discoveries on our system and as you inevitably run into roadblocks. And so I think that's something where I think my short answer to that is try out the systems, tell us what works, what doesn't, what's idiosyncratic, and then at least at Cerebras, I think we're very open to working on co-design projects for hardware and software in the future, and working on research collaborations to help to really participate in helping identify those long-term trends.
Thank you. So, Virender, you wanted to ask a few questions? Yes, please.
Okay, so
Take a microphone.
So just related to the vendor lock-in, Yuri had mentioned earlier, I don't know if anyone picked it up, but he had this Chasm API. And one thing I like about it is that it takes different hardware vendors from the quantum computing industry. And they have so basically it's like a flag which says, oh, if you're using Rigetti, or if you're using IBM or whatever, right? So it's a C++ API that allows you to switch your back end. And those hardwares are very much like in your industry. They're very different from one another, but it allows a developer potentially that is using C++ code to target those backends. And that, I think that was developed at Argonne or something. So is there any maybe hope of that? Have you guys as an industry thought about that, hey, I'm developing this Gaudi tool or hardware and I have Cerebras, and there could be the case that they can both be co-located. But now the developer and, if costs are going to be like, how are we going to port, or how are we going to actually, try to offload or something, off to these different. So that's kind of like another approach. So it might not be that type of model, but maybe a common API in its early stages that's probably saying, hey, you can do like BERT on two different, hardwares. It's the same problem. I mean, you guys showed that all we can do BERT, right? But can you like have instead of using PyTorch, you have some type of common API that makes it easier for developers on the other hand. So.
For sure. And I'll keep this one short because I have a feeling my colleagues will also want to chime in. But I think, at least on the ML side, we're looking at moving our backend to support MLIR, which is an open source machine learning intermediate representation that was, I think, initially launched by Google. But the idea there, I think, at least in my mental model, is sort of similar to what you were talking, at least for the deep learning use cases. That is, I can come at an intermediate like MLIR from multiple frameworks, PyTorch, TensorFlow, JAX, others, and then target multiple hardware backends on the backside and sort of maximize ease of transportability across different frameworks and backends. I'm 100% supportive of initiatives like that, and at least Cerebras are moving towards that. I'm not sure if there's sort of a moral equivalent that's emerging in the HPC space for applications that might be written, say, in C++ or Fortran.
Yeah, our approach has been very much like you described, that we basically build out backends for PyTorch, TensorFlow, and in the future maybe some other frameworks based on customer demand that are optimized to execute on our hardware. And because those frameworks are open source, we're able to do it at any level that makes sense. I think the main challenge is twofold. Number one is to convince the moderators of TensorFlow and PyTorch to adopt our changes into the mainstream code base so that everybody gets them kind of by default, as opposed to jumping through hoops to get our back end. And secondly, our development work along those lines tends to lead, and the moderator's adoption of those tends to lag. So that tends to create some friction and issues sometimes within a large-scale development organization.
Maybe the other thing is, like, if you can switch the backends in software, can you also switch the backend in the hardware sense as well?
Yeah, absolutely. That's a model that we've embraced all along. And part of it is Intel has a history of being, at least trying to be open on a lot of architecture, software, those sorts of things. And so when you have an open specification, then it encourages other people to, target your hardware and vice versa. So it tends to be a good model. And on the purely software side, there was a question about Fortran earlier. I really don't know that much about Fortran, but I just hope that the LLVM Fortran front end gets really, really good, so it does everything you guys want, and we'll be happy to write an LLVM backend for Gaudi or Ponte Vecchio or anything else, and then everyone will be happy.
Thank you. Anyone else? So the question for co-design. Most of the innovative computer architecture technologies presented today emphasize AI/ML type applications which utilize large-scale linear algebra and matrix type computations. This is great for the AI/ML community, but not necessarily other communities. Throughout the design of these new systems, to what extent and how were you engaging with the process of co-design with the AI community? For example, a methodology for application users, software developers, and hardware designers to work together for designing future computing systems. Do you see further opportunities for co-design for other specific problems the scientific community wants to answer that may not be solvable with AI? How would you recommend us, as mostly research software engineers, engage toward development of potential future ASIC processors, and what would you ask of us during the process of co-design toward new ASIC hardware?
Okay, I can start and others can add. We definitely have a very hardware-centric perspective of things, as you all can imagine. I would say from the users, you all have heard about some of the challenges that we talked about today. Anything that you can do in terms of co-design to help us refine those assumptions, right? Particularly around, in my case, the communication bounds that I presented, the memory bounds that I presented. Any data that you all might have from running real science that's either proves or negates some of our assumptions will go a long way towards us designing Gen 2, Gen 3 versions of these things. So, short answer to a long question, but from our perspective, that really helps.
Thank you.
Yeah, I'll say it's a great question. I think at Cerebras, our system was, in a sense, co-designed from the very beginning, particularly for AI and deep learning use, and then we discovered others along the way. But I think at the end of the day, from this room, right, what we would like to know out of a co-design process is what's the shape of the computational workload and what are the bottlenecks on that workload on other architectures? What does compute and communication and memory and what does access patterns and bandwidth requirements look like? Why is it broken or why is it challenging today? And help us understand that and then as well as sort of the value or the potential impact of solving that problem is something that we might work out together. I can't say much about them today, but I will say that we are already looking several years out for our own roadmap that's directed at deep learning, and we've been approached by several others about other co-design projects for particular applications, and this is exactly how they go. We try to learn as much as we can about the problem, why it's challenging, and how well we could do with an alternative architecture, and then try to size that in terms of the cost of the effort and what it would potentially result in terms of value back to the research community or to us as a business, right, to make it solvable and salient.
Anyone else?
Right, yeah, please go ahead. Okay. So at Sambanova, I would say we are targeting deep learning just because it's a big market to start with. But if you read the original paper out of which this architecture is based on. This was, I think, plasticine from Stanford by Kunle and Raghu and their group. AI was one application, but this was mainly designed, a lot of it was also useful for a lot of database applications around ETL and a lot of those scientific applications also. I guess it's mostly about positioning a startup to focus on one market, because we have limited resources, and just sort of focusing your resources on the most dominant market makes sense. The other part of the question around hardware software co-design, I think people here have answered them. It's always important to understand what those bottlenecks are and how do you tweak tweak an architecture one time step at a time to get to where we want to be.
Thanks.
I was just going to say that I don't think any company can succeed unless they do a certain amount of co-design in quotes, with their paying customers. And Intel certainly does it. We do it. We're essentially co-designing with Google and Meta over TensorFlow and PyTorch. We're co-designing with national labs based on supercomputer designs. We're co-designing it a lot of different ways. I think sometimes what happens is that individual constituents don't necessarily realize the diversity of constituents that a company like Intel has to serve, especially when it comes to a general purpose processor like a CPU. On GPUs and on even more specialized products and ASICs like Habana Gaudi and Greco, the constituents that we work with, they really feel like they're co-designing with us. But next person who tries to add something to a Xeon is gonna feel like they're talking to a wall, just because Xeon serves so many different constituents, and we have a commercial business to defend.
Okay. Other speakers? Probably the last question, because we are at the end of an hour. And the question goes to Aurora and HPE. Can you comment on the potential of composable hardware and interconnects for GPU, such as liquid PCIe for future APC systems? It is on. Should be on.
Yeah, composable systems are things that people have been talking about for a really long time now, and we're not there yet, and it's not clear when we're going to get there. The challenge is that anytime you start talking about composable systems, lots of people get excited about it because they dangle money out there as the reason that it's better is that you're going to save money, but you start saying, well, I'm going to put my GPUs farther from my CPUs so I can rearrange which ones it attaches to, and yet some of the bottlenecks people see are some of the distances between the CPUs and the GPUs, so it's real hard to figure out how that makes sense. And the place that people get most excited about composable systems is when they can disaggregate memory from the nodes. And you've seen some papers, there was a recent paper out there by Facebook, I think, Meta, I guess. And it's like, okay, well, how many of you would like higher latency, lower bandwidth memory attached to your nodes? Everybody who thinks that's a good idea, raise your hand. Yeah. And so I don't see it yet. Moving your GPUs farther from your CPUs and farther from your NICs. I don't understand how we're going to make that perform well enough to get a real win out of it.
Thank you. Leonard?
Yeah. So if you look at the Aurora node, right, it's like we're trying to bring things in as close as possible, right? So that itself is posing a lot of challenge if you look at programming languages trying to optimize performance on the node level, right? Like essentially the architecture evolution had taken time for us to reach the performance level that we were expecting out of the node. And that's why you see Gen 5 for the PCIe to leverage the higher bandwidth, the lower latency, more memory on the CPU side and the GPU side, the high-speed interconnect. All of this is pointing to the opposite direction of composability, I would say, right? Maybe in the distant future, when you have processor and memory technology where you can distribute workloads in terms of tasks rather than memory, then that would be a possibility. But I don't see that happening right now, at least from the applications requirement that we have today.
Thank you. So I would like to thank everyone who was participating in this section, whether asking a question or commenting or answering the questions. I think we should continue the conversation over other channels because the question about co-design is extremely important. And unfortunately, it is always the case when the co-design starts too late, when major decisions has been already made. And the influence of co-design is significantly reduced after the fact, when the community cannot really influence the critical decisions for them, while maybe not very critical, but already made decision for the vendor. So we really need to have a venue for continuous conversation about future systems, and I hope that that's going to be solved. Thanks a lot.